Greetings. We're going to be talking about categorical logic, specifically about statements in categorical logic this evening. Now I'm going to say a little bit about sort of the general field. Some of the material we're going to go over sounds a little bit dry, a little bit difficult, lots of terms, lots of distinctions to absorb, lots of relations to remember. The main thing I want to say is that categorical logic, which we'll be looking at this week and also in the next chapter, which we'll be working on next week, is really a rather remarkable achievement. It was really, so to speak, the first complete theory of logic that was ever worked out. And many people, up until sometime in the 19th century or thereabouts, considered it a complete theory in the sense that it would cover every valid argument. It's well worth spending a little bit of time getting used to it and figuring it out. We've already been introduced to categorical statements. A categorical statement is one that just relates to categories or classes of things. For example, trees and plants. In order to understand categorical statements, the way they play a role in categorical logic, there are three important words that you need to remember. The three words are just all, no, and some. The reason you need these three words is because when you've got a statement about trees and plants, and you want to bring those into relationship to one another, you want to know if you're talking about, say, all trees. Are all trees plants? How about no trees are plants? How about some trees are plants? In order to have some definite statement, you need these words or something that amounts to the same thing. For example, we can have all ducks are animals. No humans are horses. Some soldiers are cowards, and some particles are not charged. Those are all, as so far as I know, true statements. And there's an example of each of the things that you can do with these three important words. First, you can say something about all of a member of a class and say they're related to some other class. Second, you can say something about no members of a class or category, like no humans are horses. You can say something about some of the members of a class. Now remember, when we use some in logic, that means at least one. It doesn't guarantee that there are any that it doesn't apply to. Some soldiers are cowards. If there were only one soldier who was a coward, that would be true. If every soldier was a coward, it would still be true that some soldiers are cowards. And then we can make another statement, another use of some. Some particles are not charged. Now you may notice that we've got two that seem to say something positive, that assert something. All ducks are animals, and some soldiers are cowards. We've also got two that seem to say something negative. They deny something. No humans are horses. Doesn't say what humans are, but none of them are horses. And some particles are not charged. Doesn't say what else they are other than charged. It just says that they're not charged. So you've got two statements that you can make from these three terms that are negative in form, and two statements that are positive in form. If we're clear on what a categorical statement is, we can start trying to take it apart. Every categorical statement can be divided into four parts. There's first a quantifier. This is a word like all, or no, or some. It tells you how many or how much. It tells you the quantity that you're talking about. which is why it's called the quantifier. Second is the subject term. This is what you're talking about. For example, if you're talking about all trees are plants, trees is the subject term. It's the subject of the sentence. Then there's a copula. This connects the two categories in the sentence, in this case, trees and plants. The copula is going to be either are or are not. It's the verb phrase that connects the subject and the predicate. And last, there's going to be a predicate term. In our case, plants. If all trees are plants, then plants is the predicate term. So, you can spell out a categorical statement like this. All ducks are water birds, to use another example. All is the quantifier, ducks is the subject, are is the copula, and water birds is the predicate. Every categorical statement can be put into this form. Of course, they won't be all statements. Some of them will be something like no ducks are fish, or some ducks are white, or some ducks are not black. They can have different forms, but they all have this basic structure: a quantifier, subject, copula, and predicate. Those four in that order. Now, when we've gotten this far, it's time to go on. And talk about A, E, I, and O statements. This is not really new. We've just talked about these four kinds of statements. These are just new abbreviations for them. Where did they come from? That's a long story. But let me give you a little hint. I think the categorical logic, the standard traditional categorical logic, the kind that we're looking here, at least some of the ways that it's presented, bears all the earmarks of young boys, probably 15 to 20 or 25, in universities and monasteries being made to learn this stuff. And they sit down and they figure out little memory tricks to remember all the distinctions. Anyhow, that's where this comes from. And there are these four basic kinds of categorical statements. Using S for subject and P for predicate, you can say an A statement is all S or P, with an example, all trees are plants. You've seen that example before. An E statement is no S or P. No plants are animals, for example. An I statement is some S or P. For example, some trees are oaks. And an O statement is some S are not P. That is, to use our same example, some trees are not oaks. Again, notice you've got two of these that are affirmative, like all S or P and some S or P, and two that are negative, that deny something, no S or P and some S are not P. You've been introduced already to the idea of stylistic variants, particularly regarding if-then statements or conditionals. Well, in addition to conditionals, there are stylistic variants on practically every common statement or every common kind of statement in logic. For example, for A statements, these are all statements, all something or something else. Let's take a look at these. How many ways can you make an A statement? Here are some. Every cat is an animal. Each cat is an animal. Any cat is an animal. If anything is a cat, then it's an animal. Things are cats only if they are animals. Only animals are cats. All of these mean one basic thing. They mean the same as all cats are animals. And there are probably other ways that this list here does not include. Now you might wonder, you might detect some subtle differences in meaning, and you might wonder, why do I say they all mean the same thing? The basic answer to that is that they're all true or all false under exactly the same conditions. If you go down the list, you'll think about it, you'll realize that, say, every cat is an animal is true in exactly the same cases in which you'd say, if anything is a cat, then it's an animal. And you can compare any others of these. They'll turn out to be true under exactly the same conditions, and also false under exactly the same conditions. Now this would have to be really weird to imagine this. You might imagine that every cat is really a little robot and therefore not an animal. But if you imagined that every cat was a robot, then every single one of these statements would be false. They're true under the same conditions and false under the same conditions. That's why we say they all have the same meaning. They're just stylistic variants. They're different ways of saying the same thing. Mostly, for things like this, it's just a matter of getting used to it and thinking it through. Now I've given you a number of examples for A statements, but there are stylistic variants for E and I and O statements as well. And to get used to them, I'd like to recommend something. There's a very nice chart at the top of page 201 in your textbook. Take a look at it, get used to it, spend some time with it, and eventually, hopefully pretty quickly, you'll get to be pretty good at distinguishing stylistic variants and realizing what the standard form is for each of those. Now let me say a little bit more about corresponding statements. If you've got statements of different forms like A, E, I, and O, mostly up to now I've been trying to use examples that are true. For example, I say all cats are animals. I say some cats are black. I say some cats are not black. And I say no cats are fishes. But a corresponding statement, the idea is, what if you adjust all of the all, some, no, and so forth statements, but you use the same subject and the same predicate in each of those? Well, then you have corresponding statements. Here's an example. All trees are plants. That's the A statement. No trees are plants is an E statement. Some trees are plants is an I statement. And some trees are not plants is an O statement. Of course, those are not all true. Some are true, some are false. In fact, if you go down the list, all trees are plants, that's true. No trees are plants, that's false. Some trees are plants, that's true again. And some trees are not plants, that's false. Now what we can do with this is we can begin to look at these and try to notice some logical relations that obtain or that hold between these different kinds of statements. I'm going to introduce and talk about 3 logical Now that we have this notion of corresponding statements for A, E, I, and O statements, we can look at some logical relations. I'm going to focus on 3 of them. First, I'm going to give you a definition of the logical relation, and then we'll fill in with some examples. First, contradictory statements. 2 contradictory statements cannot both be true, but they also cannot both be false. Second, there are contrary statements. A pair of contrary statements, they cannot both be true, but they can both be false. And for subcontraries, they cannot both be false, but can both be true. Now that may sound pretty fuzzy to you at this point, but we're going to try to make it a little bit less fuzzy by filling in some examples. Let's start with contradictories. All trees are plants, and some trees are not plants. If you look at that closely, it's pretty obvious. They can't both be true, because one of them excludes the other. But they also can't both be false, for the same reason. If all trees are plants is false, then it's got to be that there are some trees that are not plants. Similarly, going from the other direction, if some trees are not plants is false, then it's got to be that all trees are plants. They can't both be true, and they can't both be false. Notice, we've got an A statement, all trees are plants, and an O statement, some trees are not plants. A and O are contradictories. I'll add, although I don't have an example of it here, that we could have contradictories between I and E statements as well. For example, we could say some trees are plants and no trees are plants. Those are also contradictories. Now let's go on to contraries. We said they cannot both be true, but they can both be false. Look at this example. All trees are plants, and no trees are plants. Those are contraries. The idea here is they can't both be true. It can't be that all trees are plants and also that no trees are plants. But they could both be false. How could they be false? Pretty obviously. They could both be false if some trees are plants and some trees are not plants. In this case, you've got a relationship between an A statement, all trees are plants, and an E statement, no trees are plants. Now for our third category of logical relations, namely subcontraries, they're slightly different yet again. They cannot both be false, but they can both be true. Let's plug in an example. Some trees are plants, some trees are not plants. Pretty obviously, those could both be true. But they can't both be false, because what would you be saying about trees if you said it's not true that some trees are plants, and it's also not true that some trees are not plants? It seems like it's got to be one or the other, either plants or not plants. So they can't both be false, but they could both be true. That's what's meant by a subcontrary. And that's a relationship between I statements, some S are P, and O statements, some S are not P. Now this gives us some basic logical relationships between A, E, I, and O terms. These basic relationships give us the rudiments of a system of logic, and in fact, they've been represented in a simple diagram showing the logical relationships that has been passed down for literally hundreds of years. We can represent these various logical relations with something known as the traditional square of opposition. Now, the traditional square of opposition wasn't always called the traditional square of opposition. For centuries and centuries, it was just the square of opposition. It only got to be called the traditional square of opposition when, more recently, mostly since the 19th century, logicians looked at it and thought they could improve upon it. But we're going to set that aside for right now. We're not going to worry about improving upon it until we've looked at it. And here it is. We've got all these various logical relations symbolized in this traditional square of opposition and organized in a way that makes them useful and handy. For example, at the four corners we've got A statements, E statements, I statements, and O statements. A being universal affirmative, E being universal negative, I being particular affirmative, and O being particular negative. And notice we've got these various relations that we talked about. A statements, all X or Y, is the contradictory of an O statement, namely, some X are not Y. Similarly, an I statement, some X are Y, is the contradictory of an E statement, no X are Y. A and E statements are contrary to one another because they cannot both be true, but although they can both be false. I and O statements are subcontrary because they cannot both be false, but they can both be true. Also notice along the sides, the vertical sides, we've got the relationship of a subaltern, and we notice that according to the traditional square of opposition, the universal claim implies a particular claim. In other words, if you know that all trees are plants, then you can also conclude a particular affirmative statement, some trees are plants. And if you know a universal negative, no X or Y, no trees, let's say, no trees are rocket ships, then you also know a particular negative, some trees are not rocket ships. Notice we've got these important logical relations all represented in this fairly simple diagram. What the diagram does is it represents what we can call immediate inferences. An immediate inference is one that can be conducted going from a premise to a conclusion without any intermediate step. We just looked at a couple of examples of that, the way in which A statements imply I statements and E statements imply O statements. There are also some other immediate inferences that can be represented in this diagram. For example, if you know that an A statement is true, you can immediately conclude that the corresponding O statement is false. And vice versa, of course. If you know the O statement is true, you can immediately conclude that the corresponding A statement is false. Likewise, you can do that with the A and E statements. If you know that the E statement is true, you can immediately conclude that the A statement is false. For subcontraries, it gets a little stickier, but you can do something there too. If you know that one of the subcontraries is false, you can immediately conclude that the other one is true. You've got a system of immediate inferences, points that you can go directly from one thing to another, a set of useful logical relations all marked out and codified in this simple diagram. Now, we will see that there's actually a remarkable amount that can be done with it. Up to this point, it may have seemed that we're just learning a whole lot of terms and diagrams and relations, and it may not be completely clear where it's going. What I want to do is to encourage you to spend some time on it, to absorb it, to familiarize yourself with it. This is a really neat intellectual achievement. For a long time, it was thought that this basic idea, this categorical logic, embodied in this traditional square of opposition, for a long time it was thought that this is all there was to logic. In large part, this was logic as it was left by Aristotle something like the 4th century BC. And as late as the 18th century, now we're talking about 2,200 years later, somebody like Immanuel Kant, a great German philosopher, was able to say, nobody has really made any progress on logic since Aristotle. This is truly a remarkable achievement. Now we'll see, especially next week, we'll see more about what can be done with it. But it's important to get some of the basics down in order to do that. And that's what we're doing this week with categorical statements and the traditional square of opposition.